Now we've been doing the antiderivative and integration. We always have to remember to add that plus c. Now in some cases, if you have some more information, you can actually solve for what that c value is. So the antiderivative of 2x would be x squared plus c. But if you knew, for example, that 2, 7 was on the original graph, then that would tell us enough information for us to be able to solve for c. So that's what we're going to look at today. We're going to look at finding the indefinite integral with the plus c, and then finding a point on our original graph to help us solve exactly what that c value is. So here we've got the derivative. It's 3x. Finding the original function then, add 1 to the exponent and divide by that exponent plus c. Now since the original curve goes through the point 2, 12, you would know that, well, when x is 2, y is 12. So if I plug 12 in for y and 2 in for x, I get an equation that the only thing I don't know is c. Doing this simple arithmetic here, we get 12 equals 6 plus c. Subtract 6 on both sides, and we find out that c has to equal 6. Now that we know what c is, we can write that our final equation must have been 3x squared divided by 2 plus 6. So these questions that are solving for c, there's always going to be enough information there that after you've found your indefinite integral, and anytime I refer to an indefinite integral, that's where it has that plus c, because you don't know what that c value is. It's not completely defined. That's why we call it an indefinite integral. And then once you plug in the value, well, that helps you find that c value, and then you know what it is exactly. So each of these questions are going to be asking basically the same thing, but let's look at the wording because I've chosen wording on each of these so that it's saying the same thing but a little bit different. So the gradient of a curve at the point x, y is x cubed minus 3 over x to the 4. So what this is saying is the slope of a curve, in other words, the tangent at any random point x, y is this. So this is just a fancy way of saying that's the derivative. The derivative is 16x cubed minus 3 over x to the 4. And it tells us that the original function passes through 1, 4. So find that equation. So I'm going to let you try this one. How did you do? First of all, I would take that equation, my derivative there, and rewrite it in a form that's going to be easier to integrate. So I change that x to the 4 that's on the bottom to an x to the negative 4. Then we're going to add 1 to each of our exponents and divide. And even though you might have been able to think that this first one was 4x to the 4, you're going to find that adding 1 to the exponent and dividing and then simplifying after is going to become more efficient and easier to do. And so you get your equation with the plus c. Now that you have that equation, you can plug in. You know that when x is 1, y is equal to 4 because it passes through the point 1, 4. You can use that information to solve for c. And then once you've solved for c, you can plug everything back into the equation to write your final answer. And so here in my final answer, I did simplify that 16 over 4 and 3 over 3. And sometimes you can be given information like you're told the second derivative. And you need to work backwards once would get you back to your first derivative. Working backwards again, integrating again, would get you back to your original function. So here, we're given that the second derivative is 12x minus 2. The point 2 comma 13 lies on the curve, and the gradient of the curve at the point P is 23. So we need to find the equation of this curve. Well, if the second derivative is d2y dx squared, if we work back once, we would get the first derivative. So how do we work back once? We would integrate, add 1 to the exponent and divide by that number, minus 2x plus c. Now, do we have enough information to solve for c already? Yes. Now, what information? Are we going to use the point, the 2 comma 13, or are we going to use somehow that the gradient is 23 at this point? So again, we have to think, what does the derivative tell us? The derivative is the equation of all the slopes. The point, 2 comma 13, that's a point on the original curve. That's not a point on the derivative necessarily. So we're going to have to use that the gradient at the point P is 23. Well, if we're using that, the gradient at the point P is 23, what does that mean? It means when x is equal to 2, because that's my x coordinate on my point P, then dy dx, the slope, has to equal 23. That's what that sentence means. So that means in this equation here, I know that dy dx is 23 when x is 2. And that allows me to create an equation where the only thing I need to solve for is c. So 23 is equal to 24 minus 20 plus c. Sorry, 24 minus 4. I got a little bit excited and did some mental math in my head there. 24 minus 4 is 20. Move that over to the other side, and you get c is equal to 3. So now we know that the exact equation of our derivative, dy dx, is equal to 6x squared minus 2x plus 3. So if we want to find our original equation, we're going to have to integrate again. Integrating again would mean add 1 to the exponent and divide by that number. Add 1 to the exponent and divide by that number, plus 3x. And we already used the letter c to represent something, and we solved for c, and it was equal to 3. So if you're going to integrate twice, you're going to need to introduce a new parameter, a new variable here. And so I'm going to introduce d. And now we can use the fact that this graph passes through the point 2 comma 13. So we know that when y is 13, x is 2. So we can plug that in. And solve for d. And now that we've got our equation for d, we can say the final equation would be 2x cubed minus x squared plus 3x minus 5.